Welcome to the session of Face and Body Modeling. I'm one of the session chairs, Frank Wang from National Taiwan University. So as a reminder, the audience, feel free to leave your questions on slido.com. You should have the instruction to how to leave your questions online so that we will be able to select your questions during the Q&As. We also like to encourage you to stay at the end of the presentation of each mini group, including the Q&As, to show the respect to the presenters. All right, so we would like to welcome the first speaker of the first paper. Thank you.
Hello everyone, I'm Luan from Hilliges University. Today I'm going to present our work on interpretable face recognition. So for this face recognition, traditionally from the input images, there is an encoder network extracting a single vector that presents the identity of the person. Even though being good for recognition purpose, this identity feature is highly abstract and it's difficult to understand by human. So for example, when we try to compare two images of Tom Cruise, the traditional system can still identify they are from the same person, but without any concrete reason. In this work, we try to propose to learn a feature such that elements are associated with local facial bar so that we can understand why they give such decision. With our proposed system, where there are local chains in the input images, only a few features will be changed. For example, in the second row, the eye classic only change the filter number 3 and number 4. Meanwhile, the other activation maps are still the same. So how do we learn such system? Starting from the traditional pipeline to associate its filter with the facial bar, we will first build a hypercolumn descriptor phi by creating feature at different segmented level. Then it will be passed through a set of convolution filter F, on which we will employ our proposed spatial activation diversity loss SAD to make convolution filter to be specialized. Furthermore, we also employ another branch of our network apply on the occlude version of the same input. By comparing the identity feature between the two branches, we can also define another loss function, and which can be explained later. So now let's take a look at the first function, loss function, spatial activation diversity. We would like to encourage them to be orthogonal of the filter and of their response. This orthogonality makes the filter respond to different image structure. For feature activation diversity loss, with two features of the input face image and occluded version, we first compute their difference and then we mask out the elements with big difference. Those elements supposed to be the element associated with the occluded version. The FAD loss will try to minimize the difference between the two identity vectors among the remaining elements. Here are some results. In this slide, we visualize the average location of feature activation. In our model, each filter sticks to the specific facial location, so their average location spread out around the face. Meanwhile, the conventional CNN, each filter only usually destroys the whole face, so it activates in a random position. Here we also try occlude one facial region and try to analyze the feature change in the features. For our model, indicated by the red line, only a subset of the feature associated with the occluded region have bit different. To better show the association between the filter and the facial part, we also visualize the feature chain when covering different facial regions. It is clear that the location of the feature chain around the occluded area. The semantic feature of each filter also show when visualize feature activation for each filter. For different persons, when activate, the same filter usually activate at the same facial location and following the pose of the face. For quantitative evaluation of on-face recognition ability, we test our framework in different backbone networks, including CAPTCHA and ResNet50. The observation here is that we still maintain the recognition ability in the normal test set, but we also have improved on the occlusion recognition. Here we also show another application of our network by partial phase retrieval. So here we can retrieve the phase using only the parts of the images. At a conclusion, our model learned from data structure phase representation, where each dimension activate on a consistent segmented phase part and capture its identity information. We decide two loss function enable the proposed method, and our model can also improve robustness to occlusion in phase recognition. So, for more detail, will be welcome to our poster.
Thank you.
So good afternoon, everyone. My name is Xiaobo, the first author of this paper, combining deep face recognition with noise labels, and I'm a researcher from JDA Research. First, let's review the recent progress in deep face recognition. Current methods like centralized, verified, and archivize many focus on designing loss functions to learn discriminative features. However, all these methods are based on the assumption that the training data is well labeled. Which is very difficult in practice. For example, MS-31 contains two kinds of noise labels. Label flip means that faces have been erroneously given the label of another class within the dataset, while outline means that faces do not belong to any of the classes under consideration, but mistakenly have one of their labels. It is well known that noise labels will degenerate the robustness of the learned same models. To solve this problem, current method can be divided into two categories. One is the offline memory washing up the noisy labels, and the other one is online detecting noisy labels. Although the above approaches have achieved promising results, in some cases, they cannot detect the noisy labels effectively and accurately, especially for large-scale face recognition problem. They are not aware of the errors accumulated issue caused by the sample selection bias. They ignore the importance of clean samples for learning discriminative features. To address the above limitations, in this paper, we proposed a novel co-mining framework, which uses two-peer network to combine the clean faces. Specifically for the detected noisy faces, they will be dropped because they may deter relative performance heavily. For high confidence clean faces, we exchange them to alleviate the accumulated errors. While for clean faces, we rewrite them to learn discriminative features. For the noise label detection, we use the arc-solid loss as the baseline, assuming that the noise rights are m the minibatch size. Each peer network view its small loss samples as the useful knowledge, and drops about r times m numbers of big loss samples as the destructors. For high confidence clean faces exchanging, we update the parameter theta1 by using the high confidence clean faces selected from its peer network theta2. So if we directly feed the noise back to its safe network, the errors will be accumulated. That's why we expect to exchange them. For clean faces rewriting, we rewrite the baseline arc probability by using a new rewrite function gmu. In face recognition, it is very important to perform an open site evaluation. That is, there should be no overlapping identities between training sites and test sites. To this end, we carefully remove the overlap identities, and the refined training sites are denoted as shown in the red box. We then conduct ablation studies on the synthetic data sets with different noisy rights. From the values, we can see the effectiveness of our different strategies. Moreover, we also evaluate our method on the real-world benchmarks. From the tables, we can see that our method is generally better than state-of-the-art alternatives. The last part, conclusion. We identify the samples as three parts: the noisy phases, the high confidence clean phases, and the clean phases. We propose a novel core mining framework which employs two peer networks to detect the noisy phases, exchange the high confidence clean phases, and revise the clean phases in a mini-batch fashion. We emphasize the open state evaluation and conduct extensive experiments on both synthetic and real-world benchmarks. Code and the refined training set will be released on my homepage. And thanks for your listening. So if you have any questions, welcome to our poster section, and our poster ID is number 2021. Thanks.
Thank you.
Hello. It is my pleasure to present on behalf of my collaborators our work on few-shot adaptive gaze estimation. This work was done during my internship at NVIDIA Research. Conventional eye gaze estimation is often performed in controlled environments. Our work concerns the task of gaze estimation in the wild, where we're using RGB input from a single unmodified camera. Such challenging imagery require large CNNs, and in recent years much progress has been made on the MPI eye gaze benchmark. Here we show cross-person evaluations, where the final test person has never been seen during training. To go beyond the performance of these cross-person methods, we must be able to consider the person-specific factors in gaze estimation. For example, the variation in eyeball position and size, and the angular offset between the visual and optical axes in the eyeball. These values cannot be measured from appearance only, and hence usable eye tracking requires manual user calibration. However, adapting CNNs is very challenging due to overfitting in the low shot or the low K-value cases. And this can be seen with previous person-specific methods, which perform only as well as their cross-person counterparts. With 2,500 calibration samples, we can get a performance of 2.5 degrees, but this is inconvenient. So, can we close this gap with few-shot learning? We embrace this challenge and introduce phase. Phase trains on in-the-wild data of almost 1,000 participants to first learn a rotation equivariant gaze representation. Then we perform meta-learning, where the meta-learner is in the form of an adaptable network. In the final stage, we take data from previously unseen people and create one model per person in the test set to finally yield our model for evaluation purposes. Let's first talk about DTED. DTED training begins with a pair of images from the same person. One image is embedded into 3 latent spaces: appearance, gaze, and head pose. And then the gaze and head pose codes are rotated based on known differences, with the appearance code passing through. The decoder output is then guided with an L1 loss, with the gaze code further supervised with additional loss terms. Our DTED is able to learn rotational equivariance with respect to gaze direction and head orientation, with clear disentanglement between the two. In addition, our gaze representation is compact and task-specific. Now, let's talk about our meta-learning. Our learned gaze embeddings can be used to train an adaptable gaze estimator. To do this, we explicitly learn a few-shot learning algorithm that optimizes the generalization loss. At every meta-iteration, we take a few-shot samples from a person and compute the standard gaze loss to then perform a pseudo update of the parameters. After the pseudo update, we compute a within-person generalization error on new samples from the same person. And the final meta update is with respect to the initial model parameters. At test time, we tune the learned model with an unseen person's data to yield our final person-specific model. So, how do we perform? Using just our d-TED with naive fine-tuning results in overfitting with very few calibration samples. And when applying MAML, the overfitting issue disappears. The final phase method with within-person embedding consistency yields significant performance improvements across all values of k. Phase is also better than the pink curve when using MAML with features from a dense net that was trained only on the final gaze task. And with as few as 3 calibration samples in particular, we see huge improvements in performance compared to the baselines. In the landscape of related work, we make a noticeable improvement. And what's more, we find that even with 1 calibration sample, we can outperform the latest related work. We found that our phase approach, with its representation learning and explicit learning of a few-shot method, yields tremendous performance improvements. Our results on in-the-wild data indicate that phase could apply to the personalization of domains, such as hand gesture recognition and effective state estimation. If you would like to check out our few-shot calibration demo, which you should, please stop by our poster at number 22. Our code will soon be available on GitHub. Thank you.
Thank you. So now we would like to welcome all 3 speakers up to the stage. And also, if the audience have any questions, feel free to approach the microphones. All right, so yes, please.
First, does it work? Yeah. This is for the first paper. You show the figure with different filters that you see different regions of the face. So you saw that the nose, eyes, and the mouth were emphasized, but also there was the forehead and the chin. Does that mean the network takes that as high-level representations as well, the chin and forehead?
Yes, we see a feature across the face, so there are some feature on the forehead, also have some feature on the chin. Yes.
Okay, thank you.
Okay, any other questions from the audience? If not, we got some questions from Slido. So for paper number 2, so one of the audience asked, are you able to utilize the negative labels during your training?
The native labels we have considered by the rewriting function gmu. So it is the details are in the formulations. So maybe we can discuss it at this poster section maybe for this question. So we have considered it. So in the formulation 4, I guess in our PPT. Yeah.
I see. Thank you.
Thank you.
All right. For the third speaker, the question is, what is the inference time of your pipeline? So can it be applied to real-time lower power embedded system?
Potentially, yes, especially if you swap out the backbone. And if you come to watch our demo, I don't have the exact figures, but you will see a live demo that actually works.
Okay, thank you.
So I have a question to the first speaker. So the first speaker, so your approach learns about features that are associated with fragments. What about overall face shape? Like, is it like round, long, etc.?
I think if the feature for a bigger region, maybe like it have their feature for 2 eye, maybe it will the average location maybe in the middle of the 2 eye. Maybe if it's try to describe the whole face, maybe in the middle of the face. I think so. Yeah.
Okay. Thank you.
Okay, we also got a quick question for paper number 3. So the question is, how did you get the ground truth for your gaze?
This has been provided by multiple public data sets. The specific ways you just tell people to look somewhere and you know where that point is in 3D. There are very many ways to ensure the quality of that data.
All right, thank you.
On that note, one more question to you. So can you comment if some elements of the approach can be used for unsupervised adaptation?
That's a very good question. I'm not fully sure. Semi-supervised, perhaps. Not entirely sure about unsupervised.
Yeah, all right, so time's up. Let's thank all the speakers. And please, the next mini group, please come to the first row chairs. Thank you.
Okay, let's welcome the first speaker.
Hi, my name is Oran Gafni. I'm a researcher at Facebook AI Research. and I'll talk about the de-identification work I did with Lior and Yaniv Taigman. But first, some motivation. Large-scale face recognition is now a publicly available technology, enabling tracking and identification to be performed in real time. Recent advances and potential abuse of face recognition technology invoke the need to better understand methods that successfully deal with de-identification. In this work, we address these privacy concerns. The goal is to distance the identity of a given person, making that person unidentifiable to both humans and state-of-the-art face recognition systems. We propose a method for fully automatic video modifications in real time. For each sample, the original video can be seen on the left, the de-identified on the right. At first glance, the videos might seem identical. However, the perceived identity, as expressed mainly by the altered nose, eyes, eyebrows, cheeks, and lips, is completely changed, while the pose, expression, and illumination conditions are left unchanged. We present our results on a diverse data set in terms of gender, ethnicity, and age, dealing with occlusions and excessive motion. I'll let you enjoy the rest of the samples. We applied a state-of-the-art face recognition system on the de-identified faces in a ranking experiment. Identification is performed out of the 54,000 people in the ArcFace verification set. The table reports the ranking of the true identity as perceived by the face recognition system. The ranking of the true person in the original video shows an excellent recognition capability, correctly classifying most of the frames as the top one result, as seen in purple. For the de-identified frames, despite the large similarity to the original ones, the rank is typically in the thousands, as seen in green. We applied an additional face recognition system, benchmarking our method's ability to impair the true positive rate, which is the rate of correctly classifying two images of a person as of the same person, while one of the images was de-identified. The rate drops from almost 99% to less than 4%. To provide further intuition as to what does it mean to distance the identity of a person, we demonstrate our ability to control the hyperparameter lambda, which is the distance magnitude. Given the source image on the left, the gradual shift in identity can be seen as we progress to the right, which correlates to a stronger lambda. This method is the first one to be demonstrated on video, as it is the only one to preserve the pose, expression, and illumination conditions, and produce natural-looking faces in high resolution. The architecture is based on an adversarial encoder-decoder where we concatenate the descriptor of a face classifier to the latent space, achieving a rich embedding. This provides for both accuracy and consistency in the generated identities. This enables us to work in real time, requiring a single image per video, while retraining for new identities is not required. We employ a masking process to blend between the source and generated images. This both provides for more natural faces as they are blended with real ones, and the network does not need to learn representations that are not interesting, such as background or hair. We use a multi-level perceptual loss to tie between the source and generated low and mid-level activations, while distancing the high-level activations, which are the identity. This provides for a direct loss over distancing the identity while preserving the pose, expression, and illumination, which are the low and mid-level abstractions. Additional details can be found in the paper and in the poster session, number 23. Thank you very much.
Good afternoon, everyone. I'm Wenqi from Chinese Academy of Science. Today I'm going to present our work, Face Video Deblurring using 3D Facial Price. Face video deblurring aims to recover sharp faces from blurred videos. Existing face deblurring methods usually focus on uniform blurs. However, real-world videos often contain special variant blurs. To solve this problem, some dynamic scene and video deblurring methods are proposed based on segmentation of pixel-wise kernels. Nevertheless, these methods struggle to deblur face videos, since these videos often involve post-variations and non-uniform blurs. Our motivation is that 3D face reconstruction can generate high-quality faces, whether the input face is sharp or blurry. Now, let's recall the 3D face reconstruction, which recovers 3D shapes of faces from 2D images. The widely used method for parametric 3D face modeling is the 3D model. Usually, we can derive a deep network to regress the face-relevant 3D coefficients for an input. With the extracted coefficients, we can construct a 3D face shape and texture using identity, expression, and texture information. Then, we can project the 3D face onto 2D image plane with the regressed pose and illumination, and obtain a rendered face for the input. In fact, we found the 3D face reconstruction can generate sharp edges and structures, even the input is blurry. We think the main reason may be that blur cannot change the information over face expression and pose. Therefore, in this paper, we propose to use 3D facial price to guide face video deblurring. Given a blurred face video, we concatenate 5 consecutive frames in the input layer. Then we use a ResNet to regress the 3D coefficients and render a sharp face for the central frame. In addition, we employ an encoder-decoder for the deblurring branch using 5 consecutive frames. The multi-frame inputs provide motion cues and therefore lead to better performance compared to single image input. To leverage facial price generated by the 3D reconstruction branch, we concatenate the rendered face with the first convolution layer to provide the spatial position and intensity information over the facial components. To impose the identity information, we also concatenate the identity vector to the last layer of the encoder while reshaping and zero pending. For the loss function, we propose a L2 loss for the rendering branch so that the rendered face region close to the ground truth face. In addition, the training loss of the deblurring branch is the MSE difference between the network output and the ground truth frame. Now, we evaluate the proposed face video deblurring method. We first conduct an ablation study of synthetic videos using 300 VW dataset. As shown, the baseline method without using 3D price tends to generate some artifacts. By adding 3D price, the result exhibits clearly and sharper facial structures. The quantitative results in terms of PSNR, SSRM, and identity similarity also demonstrate the effectiveness of our 3D facial price. This is quantitative results of the synthetic videos. Our method performs better than other deblurring approaches. Similar results can be found on blurred videos synthesized from another face video dataset. We also evaluate our algorithm on real-world face videos downloaded from YouTube. As shown, conventional uniform-based methods generate artifacts in the deblurred results. Even the recent video deblurring methods cannot remove blurs well on real-world videos. To summarize, in this paper, we propose a face video deblurring method by exploiting facial structure. Our estimated 3D facial price provides both spatial and visibility information of facial components. The code is available at our website. Thank you for your listening.
Hello everyone, this is Jiandan Park from the Chinese University of Hong Kong. Here I want to represent our work on 3D face reconstruction from a single image. Here the problem is that we want to construct a 3D face model given a molecular image with human face aligned in the center. For well-captured frontal faces, we have good algorithms to reconstruct vivid models while applying to complex pictures taken in arbitrary environment. Those may not work well. First, complicated circumstances such as large poses, occlusions, extreme expressions, and dark lights make the task pretty hard. Second, different from facial landmarks that can be manually labeled, lacking perfect reconstruction ground truth mesh geometry, which is obtained by optimization-based model fitting, impose more difficulties on the regression problem. So in order to solve those previous problems, we proposed a two-stage network structure. The first stage is to use CycleGAN as a domain adaptation, changing an unpredictable image into a synthetic image. The second stage is a direct vertex regressor that predicts each vertex position of the final meshes in an order of texture coordinates. This semi-supervised framework is finally end-to-end trained without any real images ground truth shapes. For the CycleGAN part, we have two normal modifications. Previous works use this network as data augmentation. However, the quality of the two directions is not equal. From real images to synthetic image, which is an information removing process, can perform quite well, while the inverse generation, which needs to add summarized background and occlusion information to synthetic image to get real one, sometimes give artifacts. Therefore, we integrate the translation into the whole training framework. As for retaining shape information, we use the pre-trained landmark network to specify images before and after generators to have consistent landmarks detected results. For the shape regression network, a UNet shape network is utilized. Output vertices are organized in the UV map that is suitable for convolution. The loss function consists of three components: the ground truth vertices, smoothness, and edges. Here we define edges as normal vectors of output with dot product of viewing directions less than a specific threshold, and force each edge of the certain face part close to ones of landmarks we detected. This is the semi-supervised logic which do not use information of ground truth and do not need any prediction of texture information. The smooth loss is just the Laplacian operator of the output vertices map, which can force the mesh to be more smooth. After we train the two networks separately, we cascade them together and perform end-to-end training. The intuition here is that although we have transformed all the images into synthetic domain, it's not necessarily the best domain suitable for training the regressor network. Besides, real images have not been supervised during training. Here we had two paths, one from synthetic images to ground truth, the other from real images to transferred images, then to final reconstruction, supervised by domain discriminator, edge losses, and other restrictions, such as the landmark losses, the smoothness. Some of the hard cases of input image datasets reconstruction results and translation results as follows. Here, most of the texture and color variants of the input images have been removed. There are results of mean error after an ICP correction with ground truth messaging and Florence datasets and AFW images with previously optimized 3DM meshes. The errors are concentrated in a small interval. A visual comparison with other methods is as follows. You can see that our methods can perform quite well on extreme cases. Another clarifying results are 3D landmarks. We can see that our post, although without any ground truth information from the landmarks datasets, can still perform competitive results. If there's any questions, you can come to our poster at 25. Thank you.
Thank you. Would all the authors come up? So please ask questions from the audience. Meanwhile, we have questions from Slido to the first author. Several people are asking about the speed of your method.
About?
The speed. How fast is it?
So it works real time. We get to 30 frames per second. And as I said, because we use only one image per video to extract the identity and distance ourselves from the identity, so that's how we can do it very fast.
Okay, there is another question to you. Given access to networks and weights, assuming that it's public, is it possible to reverse such network?
So someone asked me that yesterday, so I already got to think about it. I think that it's not a one-to-one transformation. So for example, you could de-identify people, and not every person will have their own new identities, but for example, you could be grouped into, let's say, 10,000 people or something like that, 10,000 groups, for example, and that way the reverse identification wouldn't be possible.
Mm-hmm. Thank you. So to the second author, do you have any plans to expand this method to hair and ear regions?
We didn't
Would it be possible to expand to hair and ears and head in general?
And if it depends on the reconstruction results. If the 3D reconstruction results is good for air region, it will be it will can guide for our deep learning results.
Okay, and another question is, how sensitive is your method to misregistration errors or jitter in the registration between 3D MEM and video?
Sorry?
So when you registered 3D MEM to video, there could be temporal jittering, or given that your images are blurry, the registration may not work perfectly. So how robust is your method to these imperfections?
Concatenating 5 frames in the input layer to in this paper we didn't consecutive temporal. Only use 5 consecutive frames to get temporal results.
Okay, so thank you.
All right, so thanks all the speakers. So please, the speakers for the next mini group come to the front rows.
Hi, so I'm going to present our work on 3D face modeling from diverse raw scan data. So let's talk about 3D face modeling. So then to point-to-point correspondence is a case step for 3D face modeling, would allow face scan can be organized in the same vector space. There are many classic methods, including TBS and NICB or Gaussian process fitting. And after we have the line shape, we can learn the 3D face model from registered shape, like traditional 3DMM, multi-linear model, or recent method like mesh convolution. And the learned face model can be applied to many computer vision tasks like 3D face reconstruction, face alignment, or face animation. Difference with its existing method, this paper for the first time jointly tackled the dense correspondence and 3D face modeling. We use single framework to learn face model directly from raw scan data and predict correspondence shape simultaneously. So we propose an encoder-decoder Bayesian learning framework. Specifically, given a set of unordered 3D point cloud, we first learn an encoder that estimates the identity and expression representation. And after that, to decoder, I use to decode the shape parameter to a 3D shape and also expression. So full supervision is not available due to a lack of crowd truth corresponding label. So we devised a weekly supervised learning approach with a mixture of synthetic and real 3D scan. Here we're considering two training scenarios, synthetic and real data. Synthetic data with topological crowd truth help to learn a shape corresponding prior in a self-supervised fashion. So during inference, our network can be used for 3D dance correspondence and 3D phase reconstruction. To learn a robust and highly variable 3D phase model, we construct our training data using one synthetic database and 7 real databases with a wide variety of identities, expression, and resolution. We further perform data augmentation for neural scan. So for the loss function, the overall loss constrains the vertex loss, surface normal loss using the cosine similarity, and the X ratio loss. Thus, it increases the ratio between the X length in the predict shape and the crowd truth to be close to 1. In the supervised case, given the crowd truth shape, we can easily compute the vertex or the surface normal or the edge lot using the crowd truth label. For unsupervised case, without the crowd truth corresponding label, we can still optimize the reconstruction using we use the chamfer distance at the vertex distance. With the nearest vertex indices from chamfer distance, we can observe the surface normal and the X length from the real scan, so we can still define the surface normal and the edge lot at this equation. So we first evaluate dance correspondence accuracy on FRCG database. Our method outperforms the state-of-art methods. Here are some qualitative results on 7 databases. Our method can preserve high frequency detail from high resolution 3D model. We also compare the capability of our proposed 3D phase model with the linear and nonlinear 3DMM on basal phase model. Both for identity shape and expression shape, our results are better match the deformation. We also quantitative compare our single image shape inference with prior work on phase warehouse database. We achieve the similar performance with state-of-art methods. In conclusion, we learn a robust and expressive phase model directly from a diverse set of raw scans and establish dance correspondence among them. So we divide a weekly supervised learning approach with scan leverage nodes corresponding prior from synthetic data. We also keep our high frequency detail of the 3D scan in our nonlinear 3D model. So thank you.
Thank you.
Hi, my name is Victoria Fernandez Abrevaya. I'm from INRIA, and I will be presenting our work, A Decoupled 3D Facial Shape Model by Adversarial Learning. Generative models of the 3D face are widely used for tasks such as 3D reconstruction or synthetic data generation. We consider here as input a dataset of 3D face scans, partially labeled with attributes such as expression or identity, and the goal of this work is to build a generative model of the 3D shape with a decoupled latent space, so that we can have independent controls of the different factors of variation that influence the shape, such as identity or expression. Having models with a decoupled latent space allows to incorporate semantic control in the generative process and can simplify applications such as avatar animation, expression transfer, or 3D face recognition. There have been many works on generative models that focus on modeling shape and appearance, but only a few tackle the problem of obtaining decoupled representations. If we consider identity and expression decoupling, for example, most works will treat these two as independent spaces that are linearly combined, which can present artifacts in applications such as expression transfer. Tensor models go one step further and explicitly consider the interplay between the different factors by modeling the dataset as a tensor, but these are expensive to build in practice. More recently, there have been some works proposing to learn generative models using deep autoencoder architectures, which tackle some challenges such as modeling nonlinear variations in expressions, but the representations are still not entirely or well decoupled. In this work, we propose to learn a decoupled model of the 3D face by using generative adversarial networks. To this end, we present a novel architecture in which a generator directly outputs the 3D mesh vertices, while the discrimination part happens in the 2D domain. Both domains are connected through a novel geometry mapping layer that allows to train using adversarial learning. More in detail, the generator consists of fully connected layers that, given a latent representation for each of the different factors, outputs the position of the vertices in a template mesh. Directly generating the 3D vertices allows to apply mesh regularization techniques during training and avoids artifacts that can come from mapping the mesh into the 2D domain and generating this mapping instead. On the other hand, discriminating in the 2D domain allows to benefit from recent development in convolutional networks that can stabilize training. So we discriminate a face by representing it as a geometry image, and the 3D and 2D domains are bridged by the geometry mapping layer. This layer encodes the geometry of a mesh into a 2D map I, where each pixel is associated with a location on the mesh, and the values are obtained by interpolating the vertex location using the expression shown here, where U and V are the pre-computed barycentric coordinates, and V1, V2, V3 are the 3D locations. Finally, to train a decoupled model, we consider auxiliary classifiers whose goal is to correctly guess the label that was assigned in the training set. And we consider one classifier for each of the factors of variation, which encourages the different subspaces to be independent of each other. We further apply a loss on the feature space of the classifiers to account for cases where the label of the face is unknown. We evaluated the proposed model using 3 metrics. Decoupling, which measures the accuracy of an external classificator that tells whether two faces have the same identity or expression. Diversity, which measures the average variation in the generated vertices. And specificity, which measures whether the generated faces are realistic. We compare our approach to classic linear models and 2 reset autoencoder architectures and show that it achieves significant improvements, particularly in terms of decoupling the expression subspace and in terms of diversity. We also show that each component in the loss function is necessary to achieve good decoupling results. We can see here some examples of randomly generated faces on the left, random samples with a fixed expression code in the middle, and with fixed identity code on the right. And we can see that only the proposed approach in the last row can achieve perceptually correct faces when one of the codes is fixed. Finally, a benefit of our approach is that it can be easily extended to more factors of variation. As an example, we trained a model that can be parameterized not only by identity and expression, but also by phoneme generation aspects, as shown in the figure here, where we generate 2 phonemes for 2 different identities and 5 different expressions. Thanks for your attention, and if you have any questions, please come by to our poster.
Thank you.
Good afternoon, I'm Pei Chen from Shanghai Tech University. Today, I will present our work on 3D face synthesized from a single image. This is joint work with Kenny Mitchell and my advisor, Jingyi Yu. In a nutshell, our technique first explores expression analysis for high-quality face geometry generation, and then combines supervised and unsupervised learning for facial detail synthesis. Our process mesh generation schemes can reliably handle domestic facial expressions, and whereas our detailed recovery techniques manage to produce high-quality displacement map. This is emerging interest on using real or synthetic face image as training data and apply deep learning for 3D geometry estimation. Most existing approaches do not explore emotion information and could not fully recover expression trace. In addition, parametric model failed to capture 5 geometry details. In this work, we we intend A to synthesize 5 geometry details from a single image. The first step is to obtain positive phase. We observed 3D expression exhibit a significant ambiguity. Different expressions might have similar 2D facial landmark after projection. In this example, the landmark of the two faces are extremely close to each other, while their expression parameter and shape are vastly different. We propose to use emotion features and physically based appearance features to narrow this positive parameter showing space. To obtain emotion feature, we will use a FightNet dataset to train an emotion feature predictor, we call it emotion net, and then build a feature dictionary as a prior. Details of the network can be found in the paper. State-of-the-art solutions, 3D DFA and ESPNet are able to produce reasonable global shapes and behave poorly near nasolabial and under eye bed. In contrast, our approach is more accuracy on capturing expressions. With the 3D positive phase, we set out to synthesize geometry details. We construct a new deep facial details net with two main stochastic modules, the partial detail inference module and the partial details refined module. For training, we combine supervised and unsupervised learning technique. To obtain geometry loss for measuring displacement map quality, we capture 366 high-quality 3D scans from 122 different subjects, and also augment the training data from ICT dataset. Directly fitting face image as input to the network would easily case overfitting. Instead, we model the displacement map with local patch and 64 PCA basis, and finally use the per pixel loss to recover details. Noted that the training data in supervised learning was captured under face capture device and could not emulate the image under natural lighting. We therefore applied unsupervised training in the wide facial image. To construct the appearance loss, we propose a texture space re-rendering scheme. Similar to most face rendering module, we assume a Lambosian skin reflection model and use spherical harmonics to represent global illumination. We then apply texture space modification for efficiency rendering. Here we show some results. From a single image of Robin Williams, we managed to recover a realistic 3D geometry of these algebraic actors. In those cases, our technique is able to recover very high quality wrinkle details. We also carry out some quantitative comparisons. Overall, our approach produced really low errors. Comprehensive experiments show that our technique is robust and reliable. We have released our code on the GitHub, and here is the link. Please go by proposal 2028 if you have any questions. Thank you for your attention.
Okay, so let's thank all three speakers. So please come up to the stage. For the audience, any questions, please come to the microphones. Or you can leave your questions on Slido if you would like. So I think for the first speaker, so you choose to disentangle to encode your image into ID and the expression. So they are the latent vectors, right?
Yes.
So, and you call your method weakly supervised?
Correct, yeah.
So can you elaborate how, what kind of supervision you need when you train your model?
So we have synthetic data and real data. So for synthetic data, we have crowd truth. So we only use the crowd truth. You will have only crowd truth on that synthetic data. For real data, we use the chamfer distance. So it will automatically determine the correspondence.
I see. Okay, thank you. All right, so for the second speaker. Right. So your model starting from the Z, the latent vector inputs, right?
Yes.
And you also have the ID and the expression latent vectors.
Yeah.
So are they discrete code, or how do you select such inputs?
No, they are continuous. And during training, they are sampled from a normal distribution randomly, and they are fixed. So, for example, we decide that the expression happy will always have this continuous code. And then the interpolations in between, they are learned during training.
Okay, so and what kind of supervision you need during training?
So we use partially labeled data in the training set. So the identities are fully labeled. We know this is person 1, person 2. And we know about 10% of the scans have the expression that it's happy, sad, etc., etc.
Right, thank you.
Question to the third speaker: how temporally consistent are the results? Did you try to run it on a video or more in the wild? Have you tried running your approach on a video?
Oh, yeah. For the unsupervised training, we will estimate the lighting and albedo, also the proxy mesh. Yeah.
And are these fine-grained details consistent?
No, it's not consistent. The 5 geometry detail. The 5 geometry detail is inferred from the network and then apply the displacement match to the temporal the information, for example, the lighting and the texture, and then to construct unsupervised loss and backpropagate the network and then update the weights. Yeah.
Okay, and we have a question from Ivan to all speakers, whether any of you have tried to use your methods to augment face recognition data methods, and whether it works. Have you tried your methods to improve face recognition? Synthesize synthetic data to improve, augmentation synthetic data to improve face recognition?
Actually, in the unsupervised learning, we did not use the capture data.
But you can synthesize new data?
Yeah, for sure.
Maybe any of you have tried it?
I think time's up.
Okay.
Yeah, right. So I think time's up. So let's thank the speakers again. And please, the next mini group, come up to the front.
So, good afternoon, everyone. It's my honor here to introduce our work S-squared gain, share aging factors across ages, and share aging trends among individuals. All the authors are from the Institute of Computing Technology, Chinese Academy of Sciences. I'm the speaker, Zheng Lianghe. At first, let's talk about task, face aging and rejuvenation. This task aims to predict the future or recall the past of a given phase. Specifically, for example, aging aims to translate the young face image to an older one. In contrast, rejuvenation aims to change an old face to a younger age. But before introducing our method, we should first discuss an essential question, that is, how does the human age? Let's look at the example. Harrison Ford ages by receding gray hair, while Arnold Schwarzenegger ages by receding hairline. That is to say, these two persons have distinct aging manners, and we call these person-specific aging manners as their personalized aging factors. Besides, there are also common aging trends between them, such as that both their wrinkles become more, longer, and deeper. Therefore, we have a basic but very important observation that the natural aging of human face contains two key elements. The first is the personalized aging factors, which describe one's unique aging manners. And we believe these personalized factors are encoded in our genes, which would not change during our whole life. The second is the common aging trends, such as deeper wrinkles and looser skin, which are followed by all of us. Therefore, based on this observation, we propose a method to simulate the natural aging of human face. First, our model shares the personalized aging factors across ages. Second, our model shares the common aging trends among individuals. For example, Haoxiang masters have their own personalized aging basis, which contains the information of their own aging manners. And this personalized basis is shared across ages because it is modeling the aging genes, which are determined since we were born. Then we have a common aging transform for each specific age, which is shared by all persons. Specifically, when we apply a 25-year-old transform on their basis respectively, both of them will be translated to 25 years old. Similarly, the 55-year-old transform can change both of them to 55 years old. Next, let me introduce the concrete modeling of our method. First, the personalized basis is extracted from the input phase by a deep encoder. Then, different aging transforms corresponding to different ages are respectively applied on this basis to generate age-specific representations. Finally, these representations are decoded by a common decoder to generate faces of different ages. To train the model, we use an adversarial loss to ensure the fidelity, as well as the age loss to ensure the accurate aging. Besides, there is an L1 reconstruction loss to guarantee the identity preservation. As can be seen, the personalized basis is distinct for different persons, but shared by all ages, while the aging transforms are distinct for different ages, but shared by all persons. And these two key parts form the main novelty of our method, which are termed as S-square module. And these are some of the visual results of our method. As can be seen from the second line, our method can achieve favorable continuous phase aging. Finally, let's make a conclusion. In this work, we provide a new perspective of natural aging, and based on this perspective, we further design an effective phase aging framework which achieves high fidelity continuous phase aging. Our poster ID is 29, and welcome to our poster for more details of our work. Thank you.
Hi everyone, my name is Ben and I will talk about the Puppet GAN, the model we developed with my amazing collaborators from Boston University and Google. Our model learns how to perform a specific semantic manipulation of real images using only synthetic supervision. So for example, if we fit it with demonstrations of what it means to transfer a mouth expression from one synthetic image to another, our model transfers this knowledge to a real domain and successfully manipulates mouth expression of real humans, again with zero supervision on real faces whatsoever. Now, you can see that it successfully preserves all other attributes of real faces, such as lighting and orientation, and successfully manipulates the mouth expression only. Our model is not limited to mouth expression and can be applied to any attribute that could be modeled synthetically. So, for example, if we provided with examples of what it means to modify lighting on synthetic faces, it successfully learns how to manipulate lighting on real faces. It preserves all other attributes of real inputs, such as identity and expression, and completely ignores the lighting of the real input, which is exactly what we want. The lighting of manipulated images is determined solely by the synthetic inputs. We're not limited by the phase domain either. For example, we could learn how to rotate and resize handwritten digits from demonstrations on typewritten digits. Our model successfully transfers this knowledge across domains as well. So here you will see how it learned how to rotate real digits from synthetic demonstrations while mostly preserving class label and style. Again, it transferred this knowledge across domains without any supervision on real data. So to summarize the task that we're proposing and solving in our paper, at train time we use real data with zero supervision and triplets of synthetic images that show how to manipulate the attribute of interest in isolation. In this example, images of real humans with no labels attached to them, and examples of how to combine mouth expression with other attributes of synthetic 3D face renders. test time, we used the resulting model to manipulate the same attribute in real images, using synthetic images to specify the new attribute values. We jointly train a shared disentangled autoencoder. We use explicit supervision on synthetic domain, and on real images we enforce several common sense constraints for how multiple consecutive attribute manipulations should interact with each other. This gives us a model that can manipulate real images using very crude domain models. Just like a puppeteer uses their hand, a crude model of a body, to manipulate a puppet, hence the name PuppetGAN. Here, the model is trained on synthetic renders and applied to face crops from 300 faces in the wild dataset. We just crop faces, apply our model, and paste them back without any stitching applied whatsoever. You can see that the orientation, lighting, and other attributes of face crops are mostly preserved, and only the mouth expression is manipulated. This specific original video is biased. The person leaned towards the microphone while speaking, so the mouth openness and the microphone positions are very strongly correlated. Our model fights against this bias in the dataset, and that causes some glitches. But other attributes, even those not present in the simulation, such as hair or glasses or eye openness, are all preserved in manipulated images. Chin artifacts would not be an issue if we used some stitching algorithm, but for the clarity of reported results, we did not do that. Just crop, manipulate it, and paste them back. I would like to remind you again that this model is not face-specific. It can be applied to any attribute in any domain if synthetic training triplets are available. We trained MUnit, Data, and Cyclic Assistant VIE on same datasets, and neither was able to both disentangle the correct attribute and transfer this knowledge across domains. To be fair, among these models, only Data was originally designed for this specific task. We evaluated how much the output is affected by different attributes of real and synthetic inputs. This tells us how well these models can manipulate individual attributes in isolation, and our model excels quantitatively as well. To sum up, the PuppetGAN learns how to control individual attributes in real images from very crude domain simulations. Thank you.
Hello, my name is Egor Zakharov, and I would like to present you the work that was done in Samsung AI Center in Moscow in collaboration with Skolkovo Institute of Science and Technology on few-shot learning of realistic talking head models. We present a system that can learn realistic talking head models. Notably, learning of a new head model requires just a handful of images. In this example, the model was learned from 8 frames. Once the talking head model was learned, it can be driven by the face landmarks positions. In our work, we extract landmarks by running an off-the-shelf face landmark tracker on a different video of the same person. Effectively, the learned model serves as a realistic avatar of a person. Our talking head model works well even for new view angles, not present in the few-shot training set as shown here. Our system can learn from different number of frames. One-shot learning from a single frame is possible. In our paper, we also evaluate our model on 8 and 32 training frames, which of course leads to head models of higher realism and to better identity preservation. Our approach uses a meta-learning stage, which is performed on a large data set of videos. For the results in this presentation, the VoxCeleb2 dataset is used. 3 networks are trained during the meta-learning stage. The embedded network maps frames concatenated with the landmarks into vectors containing pose-independent information. These vectors are used to initialize parameters of adaptive layers inside the generator network, which maps landmarks into the synthesized video. Finally, the discriminator network assesses the realism, pose, and identity preservation of the generated frames. The latter is achieved by having a trainable embedding vector inside the discriminator for each training video,
which contributes to the final realism score, like it is done in projection discriminators. After meta-learning, we are able to fine-tune the learned generator and discriminator on new people. Even though the generator and the discriminator networks have tens of millions of parameters, such fine-tuning is possible on a handful of examples, thanks to the good initialization provided by the meta-learning stage. First, we initialize adaptive parameters of the generator and video embedding of the discriminator via outputs of the embedded network. After that, we train the generator and the discriminator on the available few-shot train set using the same adversarial objective as in the meta-learning stage. The adversarial fine-tuning is very important for improvement of realism and identity matching. Also, it allows us to better scale performance of the approach with more few-shot training data, as well as to overcome some biases with respect to visual appearance that our model inherits from the dataset. The identity match improvement is particularly striking in the bottom example. We also show that our system generalizes to selfie photographs that are quite different from YouTube video frames that were used for training of the model. Here is one more example of the model learned on 16 selfie photographs. The face landmarks for both of these examples were calculated using a different video of the same person. Finally, we can push our generalization even further, evaluating the system on famous photographs. In each case, we automatically find people in the VoxLab 2 dataset with landmarks suitable for the animation of a particular portrait. With a certain degree of success, we can even apply the model to paintings, despite the large domain gap between paintings and YouTube videos. Also, by evaluating on paintings, we can see that despite that the model might be very sensitive to the geometry of the landmarks, and driving Mona Lisa with landmarks from 3 different people results in videos with very distinct personalities. Landmark adaptation and tighter integration of our system with landmark tracking remains future work. If you are interested, please come see us at our poster number 31. Thank you for your attention.
Thank you. Please, all speakers come up. And if you have any questions from the audience, please also come up to the microphones. There is a question to the first speaker. So the question is, have you evaluated your method, how it affects cross-age face recognition?
No, we didn't investigate our method in face recognition, but I think now our method cannot be used for face recognition because the data for face recognition should have variance by pose, expressions, age, but many dimensions, but we only change the appearance of age, but so we don't think the current method can be used for data augmentation for face recognition. But I think we can incorporate other attribute editing methods to edit the data, to edit the face by several dimensions like the pose, age, and expressions together. So I think it should be investigated in future.
But if you have an image, set of images for a person at a certain age, by applying your method, you can diversify the data set over ages, and then you should be able to recognize a person at a different age much better.
Yeah. But I didn't try that.
Okay.
Okay, thank you.
Question to the second speaker. So could you comment, so you showed like 2 types of transformations. Could you comment which transformations your method can handle well and which it cannot handle well?
Okay. The specific implementation that we had some troubles with things like lighting intensity overall, probably because of batch normalization somewhere from our experience. Other than that, it pretty much worked in majority of cases that we use it.
Can it learn 3D rotation? There is a question.
I think probably. We haven't tried, but since it successfully disentangles mouth from head rotation, there should not be any reasons why it cannot disentangle it the other way around.
Okay, thank you.
Can you also comment on how do you get your face invariant features? So you claim that your model is able to, ID invariant, right?
So while training, we provided with synthetic examples of what it means to combine a certain attribute with all other attributes in another image, and if in another image we vary the identity, then the identity of 3D model, like the shape and so on, then it learns to be invariant to identity.
All right, thank you.
Thanks to all the speakers, I think.
Yeah, we have very limited time left, so let's thank all the speakers. Right, so for the last mini group, please come to the front row. And the first speaker, please come up to the stage. Yes, go ahead.
Hello, everyone. My name is Desen Zhou. Today, I will present our paper, Host-Aware Multi-Level Feature Network for Human Object Interaction Detection. This is a joint work with Luan, Yongfei Liu, Rongjie Li, and Xuming He. The problem of human object interaction detection, as known as HOI detection, is that given an image, we aim to detect all the interaction pairs between humans and objects, as well as recognizing the interaction classes. There are many potential applications of HOI detection, such as visual question answering, activity analysis, and video understanding. Prior work of HOI detection usually adopt a hypothesis and classify strategy, which first generate proposals of human-object pairs by object detection network, and then use a classifier to determine the interaction classes of each proposal by utilizing object-level features as well as spatial configuration generated by bounding box masks or estimated human pose. However, as the interaction classes are usually defined in a fine-grained space, using coarse object-level features may not be enough for such fine-grained relation detection. This motivated us to utilize human pose to capture detailed semantic particule, which is combined with object-level features as well as interaction features to estimate fine-grained interaction classes. An overview of our framework. For each human object proposal, we extract image features by a backbone module and generate a spatial configuration map that combines both detection proposal masks and human pose. We then use a holistic module to capture object level and relation context information in a coarse global view, and the zoom-in module to capture detailed local information between semantic paths and objects. We finally fuse the holistic feature and zoom-in feature together to perform final HOI classification. Specifically, the holistic module simply takes spatial configuration map, human features, object features, and union features, use FC layers to embed them to a feature space, and concatenate them together to obtain the coarse-level holistic representation. Our zoom-in module consists of 3 components: part crop component, crop part features, and object feature. In addition, we noticed that the spatial configuration of human parts and objects is informative for HOI classification. We thus propose a spatial align component, which augments parts and object features with a coordinate map. The coordinate map encodes the relative spatial offset between parts and objects. We also use spatial configuration map to estimate a semantic attention, which is multiplied with part features to suppress the irrelevant parts for current human object proposal. We finally concatenate parts and object features and embed them to a local representation, which encodes detailed semantic particles. Our fusion module takes holistic feature to predict a local interaction score, and fuses holistic feature and local feature to estimate a local interaction score. The global score and the local score are multiplied to get the final HOI score. We evaluate our method on two public benchmarks, VCOCO dataset and HICO data dataset. Our method achieves 52.0 MAP on VCOCO dataset, outperforms the state-of-the-art method by 4.2 MAP. On HICO dataset, our method outperforms all the existing methods in two different evaluation settings. We perform ablation study on VCOCO dataset. We add our components one by one and see the consistent improvements of performance. We observe that the part crop component and the spatial align component significantly improves the performance, demonstrating the effectiveness of our zoom-in module. We show some qualitative results of our experiments. We can observe that for those fine-grained relation classes, utilizing semantic particles significantly improves the performance. We also visualize the outputs of our estimated semantic attention values. We can see that the semantic attention network is able to attend to different parts for a person interacting with different objects and different human object configurations. Thanks for your attention. If you are interested in our work, please come to our poster number 32.
Thank you. The next speaker.
Well, good afternoon, everyone. My name is Haodong Duan, an MPhil student at Chinese University of Hong Kong. Today, I will present our work, TRB, a novel representation for 2D human body understanding. Well, in traditional 2D human models, pictorial structure use articulated, rigid rectangles to represent human limbs, which mainly incorporates 2D pose, while deformable structure and contour people add additional parameters to describe human shape. These models are fitted to images with NG minimization. While in deep learning era, skeleton key point is a mostly used 2D human representation. It can be estimated accurately with big data and deep model. However, it focuses on 2D pose and ignores 2D shape. So can we incorporate 2D human shape into such a representation? And motivated by this, we developed triplet representation of human body, TRB. It incorporates both 2D pose and 2D shape, and as simple as skeleton key points. So what is TRB? TRB is extended from skeleton key points. For each skeleton key point, we define two contour key points located on both sides of human boundary. These contour points are divided into medial ones and lateral ones to make annotating less ambiguous. So we annotate contour points on these three datasets, MP2, LSP, and COCO. These datasets contain in the wild human images, which covers a wide range of human pose, shape, and granularity. So first, we try to conduct current pose estimation approaches on the TRB estimation task, and we mainly have two observations. First, contour key points are harder to locate than skeleton key points. Second, if we use TRB as extended key points, it does not improve skeleton estimation despite the richer supervision we used. Based on that, we developed TRBNet, a two-branch network for TRB estimation. TRBNet can use various backbones denoted by MS block here, and we developed various message passing modules between the skeleton branch and the contour branch denoted by MP block here. The X structure is the most naive module. It concatenates current branch feature and transformed remote branch feature to give out a refined prediction of heat map. And directional convolution, it further improves the X structure. It is used in feature transformation. It updates feature in an inside out or outside in order during one-pass convolution. By doing so, it simulates the scattering from skeleton to contour and the gathering from contour to skeleton, which makes feature transformation more efficient. While in pairwise mapping, for each pair of key points we defined, the warping between them is estimated. And then we add a consistency loss onto the estimated heat map and estimated warping. Finally, those predictions are ensembled to give out a better prediction. In this example, the right wrist is at first wrong and corrected by the pairwise mapping module. And here comes the result. On TRB estimation task, TRB net improves accuracy by nearly 2% comparing to its baseline. On skeleton key point estimation task, TRB net also outperforms its baseline and competitive to those state-of-the-art methods. On COCO dataset, when using TRB net and TRB annotation, similar accuracy can be obtained with nearly half amount of the training data, which denotes the data efficiency of TRB annotation. TRB has rich potential in application. In this example, we use a VUNet for TRB-guided human image generation. We added contour points to change the shape of human leg, shoulder, and torso in these 3 demos. Okay, that's all. Thanks for your attention, and welcome to visit our poster at 33.
Thank you.
Good afternoon, everyone. I'm Wei from Australian National University. I'm going to introduce our work, Learning Trajectory Dependencies for Human Motion Prediction. This is a joint work with Miao Miao, Matthew, and Hongdong. When you were watching The Avengers, have you ever been curious about how Jarvis can remove the suit seamlessly while Tony is moving? No matter how fast the robot can react, after seeing the human motion, there will be a delay. To act proactively, it needs to predict Tony's motion. That motivates this task, human motion prediction. Given a sequence of past human poses showing black skeleton, human motion prediction aims to generate human movement in the near future showing colored skeleton. Since it's a sequence-to-sequence problem, many previous works tried to solve it by recurrent neural networks RNNs. Despite their good performance, using RNNs to encode temporal dynamics, the past information may vanish during the long propagation path. Moreover, the frame-by-frame prediction does not encourage global smoothness of the sequence. As a consequence, feed-forward networks, such as convolutional ones, were studied as an alternative way. In particular, by regarding the motion sequence as a 2-dimensional matrix, 2D convolutional filters can be applied. However, the range of spatial and temporal dependencies captured by this model is then determined by the size of the convolutional filters. These shortcomings motivate us to develop a feed-forward method so that nothing is forgotten. The feed-forward method is used to generate sequence-level encoding instead of frame-by-frame outputs. And spatial structure of the motion sequence is captured by a learnable fully connected graph. When it comes to temporal encoding, we find that a joint trajectory of past frames is closely related to that of future frames, no matter in angle space or 3D space, so that we instead plan to predict the joint trajectories given the past trajectories. Inspired by the non-rigid structure from motion literature, we adopt discrete cosine transform, DCT, to convert a sequence of data points to coefficients of cosine functions. As to spatial encoding, it is obvious that joint movements are dependent to each other. As we can see from the sequence, when we put our left leg forward, we will always swing our right arm forward at the same time. Similar pattern can be found between other parts of our body when doing various activities. Human pose can be naturally represented by the kinematic tree, and by performing simplified graph of convolutional operation on the tree, relations between neighbor joints can be modeled. However, one joint, such as right hand, is not only related to its neighbors, but also to those that may be very far away, such as the left foot. So that we design a fully connected graph with learnable connectivities. which means instead of using predefined sparse adjacency matrix, we are going to use a learnable dense one. Put everything together, we aim to find a mapping from the trajectory of the observed sequence to the future ones. We first replicate the last observed pose t times to generate a longer sequence, and the goal now is not only to predict the future poses, but also to recover the observed sequence, which can be translated to estimate the residual. After the DCT, the input sequence is brought to trajectory space represented by H. Each row of H is the DCT coefficient of a joint coordinate or angle sequence. One graph convolutional layer consists of two operations. First, a shared filter W is applied to each trajectory to extract temporal feature, and then for every node, a learnable adjacency matrix is used to aggregate information from itself and all the other nodes. Such graph convolutional layers followed by activation functions make up of model, and the A1 distance of the whole sequence is used as loss. We validate our method on 3 different datasets: human 3.6M, CMU mocap, and 3dPW. We first show quantitative results on 3dPW. The x-axis of the graph is the future time, and the y-axis is the average angle error. The lower, the better. We also provide qualitative comparison. First graph from the left shows the angle error at each future frame. In the other graphs, the black skeletons are ground truth, baselines are showing blue skeletons, and hours are in red. Welcome to our poster number 34 for more information. Thank you.
Thank you. And we have one more speaker for this mini group.
Good afternoon. My name is Hongyang Tang. I'm honored to present our paper, Cross-Domain Adaptation for Animal Pose Estimation. I will introduce in following aspects. Previous works that focused on human pose estimation have achieved promising results. Their success are based on large-scale human pose dataset, such as COCO, but almost no work for animal pose estimation, although there are many applications. The first reason is the lack of animal pose dataset, and there are too many kinds of animals. It is impossible to provide labels for all of them. So aim to tackle cross-domain animal pose estimation problem. There are two challenges for this problem. The first is lacking dataset. The other is the gap between different domains, such as human and animals, and different class of animals. Since there is almost no available animal pose dataset to objectively evaluate the performance on animal pose estimation and to obtain basic knowledge under weak supervision, we build a pose-labeled animal dataset. Our dataset has 5 classes of animals, which are cat, dog, horse, sheep, and cow. Here are some samples of our dataset. It has been released. You can find more details or download from this link. We hope it can provide heuristic knowledge to animal pose-related tasks. To eliminate domain gap, we need to exploit some knowledge sources. They are respectively a pose-labeled human dataset and bounding box-labeled animal dataset and other classes pose-labeled animal dataset. For example, if we estimate coarse pose, the pose information of other 4-class animals is also useful. With the priors above, we propose a novel method to leverage them to facilitate animal pose estimation called weakly and semi-cross-domain adaptation. It consists of 3 parts: feature extractor, domain discriminator, and the key point estimator. The feature extractor takes out features from input image, based on which the domain discriminator tries to distinguish which domain they come from. The domain discrimination loss, DDL, is defined based on cross-entropy loss. And the pose-labeled animal and human samples can boost the key point estimator together and the supervision. So the pose loss defined as this. Finally, the overall loss of WSCDA is the weighted sum of DDL and pose loss. We set alpha times beta smaller than 0, so domain discriminator and key point estimator are optimized adversarially. The model will learn the cross-domain shared features. After WSCDA, we design a strategy called PPIO to approximate the underlying labels with pseudo-labels. We adopt an alternative training strategy. The data come from source domain and target domain. The joint training loss is defined as the sum of target and source domain loss. And the target domain loss uses a prediction of a current model as ground truth called pseudo-label. Only if the confidence of a prediction greater than threshold, we select it as a pseudo-label. This is the overall process of our proposed scheme. The final model is pre-trained through WSCDA and boosted under PPIO. Here is our evaluation results on our animal pose dataset. We compare with some pose estimation methods and some adaptation methods. Experiments show that our proposed method achieves convincing results on animal pose estimation tasks. This is a realization of our results on unseen animals included in our animal pose dataset. And we can also estimate unseen animals not included in our dataset. Thanks for attention.
Thank you. So please come up to the stage. So we kindly ask you to stay for another 3 minutes for the Q&As. Again, any questions from the audience? So if not, 1 and 2 for the first speaker. So for this first speaker, so are you able to handle multiple objects if you have such images?
Yeah, we first use object detection network to generate multiple proposals, and we deal with each human object pair individually, one by one, and then our algorithm can deal with a person interaction with multiple objects.
I see. And you talk about the multi-label relation, right?
Yeah.
So how does that relation design constructed? So you first construct what kind of
object level
right.
The representation, we crop human features and object features, and the interaction level, we crop a union, use a union bounding box mask to crop a union feature, and a detailed semantic level use pose to guide it. Yeah.
Okay, thank you.
Thank you.
Question to the second speaker. How is your representation defined for clothed people, like people wearing skirts, for example?
Sorry, can you say the problem again?
If a person wears loose clothing, like skirt or like big sleeves.
We just annotate. The annotator will annotate the contour points by guess to where are the real boundary, and they will annotate contour points on the real boundary they guessed. Yeah.
Can your representation be predicted from or be used to predict dense pose?
You mean the difference between our work and dense pose? Yeah. There are several differences. First, the dense pose, it is a 3D model, and our TRB is a 2D model. Our TRB is more efficient. It can be estimated. If you use a small backbone, it can be estimated very fast, like on a mobile device. It can be deployed on a mobile device. I think that's our advantage.
Yeah. Thank you.
Thank you.
And for the third speaker? Yeah, so a quick one is, why you choose DCT? So what is the property or advantage of using DCT?
So first of all, because DCT is a very compact representation. for a smooth trajectory, you can always eliminate the last few coefficients to almost losslessly represent the sequence. The other reason is it is already proved in the traditional non-rigid structure from motion literature. That's why we choose DCT.
Thank you.
Nice.
So thank you. That was the last session of oral session of ICCV. Let's thank all the speakers.
Thank you.
Please enjoy poster session and workshops.